Now that we get the idea of how to do a confidence interval, let's take a look at the idea of calculating sample sizes for proportions. The idea here is before we go out and take a sample, you need to know what the sample size is going to be. Now we couldn't address this earlier because we didn't have the concept of margin of error, and sample size is very much directly related to the margin of error. So in order to calculate an appropriate sample size for proportion, there's two things you must know. First, you have to know the level of significance. That's that alpha we've been talking about. And the second, you need to know the margin of error. So in other words, if you say, hey, I want to go get a sample and I need to have a confidence interval such that the margin of error is no more than 2%. I want to have my estimate within 2%. Well, that means the margin of error is 2%. Now this quantity right here is known as the margin of error. The value of V is specified by the level of significance, alpha. So when you specify alpha, that specifies Z's. So to calculate the sample size, all we have to do is take this, set it equal to the margin of error that we specify, and solve for n. So let's just do that algebraically here real quickly. So I'm going to have z of alpha over 2. I'm just going to write it as z so I don't have to keep writing the alpha over 2. Square root of p hat 1 minus p hat over n. And that equals the margin of error. So if I square both sides, I will have z squared times p hat 1 minus p hat over n equals the margin of error squared. And then solving for n, that gives me z squared over p hat 1 minus p hat over the margin of error squared equals n. And typically we don't write it like that. We'll say n equals z times the square root p hat 1 minus p hat over the margin of error, the whole thing squared. So with this information, we can say, hey, give me a margin of error, give me a level of significance that specifies z, and then I can tell the sample size. But once again, it has a problem. And the problem is p hat. In order to calculate the sample size to go get a proportion, this is saying I have to have the sample proportion. That is definitely a problem. We're back at the who came first, the chicken or the egg. So again, the problem here is this equation requires p hat to find a sample size so you can calculate p hat. That should sound confusing. So we can fix this problem. And one way to fix it is we can always use a value of 1/2, 0.5 for p hat. And that creates a safe value. Now, why is that safe? Well, we need to do a little bit of algebra here. Here's the deal. This is 0. This is 1. This is my p hat axis. This is my n axis. So I graph this as a function. Remember, z of alpha over 2, it's fixed. The margin of error is a number, it's fixed. All this is like x times 1 minus x square root, and the whole thing squared. So when I think of it that way, and like this is y, this is just a function of x, like you would plot it a zillion times in algebra. Well, notice right here down the middle is a value of 0.5. 0.5, and that results in the highest value for n. So if I use 0.5 in my sample size calculation rather than that, if I put 0.5 in, so it's 0.5 times 1 minus 0.5, that will ensure that I have the absolute largest sample size possible. Now, if I were to use like a 0.2, I would end up with a sample size down here, which if I were to actually end up with a sample proportion less than 0.2 or greater than 0.8, because you can see these overlap, then I'd be just fine. But if my sample proportion were in here somewhere, what that means is I needed a bigger sample size, but I had one that was too small. So the margin of error is going to end up being bigger than what I really wanted. So this 0.5 is a safe bet. It also results in some pretty big sample sizes. So there is kind of some take and give here. So let's take a look at this here. I want to calculate the needed sample size for proportion given the following criteria. First of all, if you look here, level of significance for his first three are always the same, 0.05, 0.05, 0.05. And then the margin of error is what changes. So if 0.05 is a level of significance, then the confidence level 1 minus 0.05 is 0.95. So all of these have 95% confidence intervals. All that's changing is the margin of error. It's like I want a tighter and tighter and tighter interval. So jump into TC stats. I will select analysis methods without data. And then on the bottom here, you see sample size calculations. And you see the top one is for mu, when I'm dealing with the mean, and there's a basic formula. And here is when I'm dealing with the proportion for pi. So I need the margin of error. And the first one I said the margin of error is 0.05. Whoops, 0.05, there we go. The point estimate for p is going to be half, so 0.5. And the significance level, alpha, is 0.05. So that would need a sample size of 384.15. Now, when we get a decimal portion there, we always round up. So I would actually get a sample of 385. Doesn't matter. If this is anything but zeros, I'm always going to go up. So now I'll repeat it with 0.03 and 0.01. So I change my margin of error to 0.03. That sample size is now 1067.07. So again, I round it up to 1068. And 0.01 gives me 9,603.65. So again, I rounded up to 9,604. Now, pay attention to this number right here, because you will see this a lot in the news. Very commonly, very, very, very commonly, you will see a margin of error of 3%, sometimes 2%, quite often 5%. And you see based on a sample size of 1,068. That's where that comes from. Now I want to repeat the same process, and I'm going to hold my margin of error at 5%, but I'm going to change my level of significance from 5%, 2%, 1%. Now, if my level of significance is 5%, then again, I have 0.95 as a level of confidence. So this is exactly the same as the first one, so this will be 385. I'm just going to go straight to rounding. This will give me a different level of confidence. This will give me 1 minus 0.02, which is 0.98. So I'm more certain. And this is 0.99. I'm even more certain. So let's see what happens to the sample size as I change the level of confidence. Now I just said, let's see what happens as I change the level of confidence. But I'm actually changing the level of significance. But really, one changes the other. So although it may have sounded like I said something incorrect, I really didn't. As I change the level of confidence, it changed the level of significance automatically changes with it. If I simply change the level of significance, that will again force the level of confidence to also change. So at 0.02, what do I get? Let's jump to TC stats here and take a look. 541.19, which I simply immediately rounded off here to 542. And when I change the level of significance to 0.01, I'm at 663.49. So again, I just immediately rounded. So what happens as the margin of error gets smaller while maintaining the same level of significance? That's referring to this. What happens? Well, the sample size gets bigger. And why does that happen? Well, if I go back to what my margin of error looks like to begin with, remember it's z of alpha over 2, square root is just going to be 0.5, 1 minus 0.5 divided by n. Actually, I shouldn't put the 0.5 in there. I should put p hat in there for right now. This is the margin of error. Right? So if I take this entire quantity while I'm holding the level of significance constant, that means this value of z does not change. If I take this entire quantity and I want to make it smaller, the only way I can make it smaller is to increase the sample size. And that's exactly what's happening here. The only way I can enforce the margin of error, which is all of this, to get smaller when I'm holding alpha constant, this is just some constant number, is to increase the sample size, which is what I saw. What happens if the level of confidence gets smaller while the margin of error remains the same? Well, that is this next one where I change the confidence level. And actually this is misworded. This is what happens if the level of confidence gets smaller. It's not. The confidence level is getting bigger here. What's happening is it's saying I'm more and more certain while the margin of error remains the same. So here's a margin of error. It's always the same. So this quantity, this z of alpha over 2, square root of p hat 1 minus p hat over n, this entire quantity has to remain 0.05, but I'm changing the level of alpha. As I'm becoming more and more certain, this value is getting bigger and bigger and bigger. If I go back to that curve, if alpha is 0.05, I may have here 0.05 over 2. If it's 0.02, up here would be 0.02 over 2. So you see I'm getting farther and farther out. This value of z is getting bigger and bigger. So this piece is getting bigger. So if this is getting bigger, but I want to maintain the margin of error, all of this to be the same, that means this has to get smaller. And the only way that can happen is if I increase the sample size. So this last question here is a small value of level of confidence increasing or decreasing the probability that the parameter value falls within the interval. In other words, if I have a 95% confidence interval as compared to an 80% confidence interval, am I increasing or decreasing the probability the parameter value falls? Well, as the level gets smaller, I'm decreasing the probability. I'm saying now I only have an 80% chance that when I build this interval that the true parameter is going to fall in there. If I increase, go to 95% or maybe a 98%, I'm saying that the probability the true parameter falls in the interval is greater. I'm more and more certain that it's going to be in there somewhere. More certain is not necessarily better, because if I don't change anything other than the level of confidence, then what's going to happen is the interval is going to get bigger and bigger and bigger. So if I have my confidence interval here, I've already collected my data, I already have p hat, I already have n. All I'm changing is alpha to be more and more uncertain. As I drew that diagram earlier, as alpha gets smaller, the value of z gets bigger. It's going farther and farther away from the center. If the value of z gets bigger, then the confidence interval gets bigger. So if I simply say, with my data, I want to be more certain, the only way I can be more certain without collecting more data is simply to make the interval bigger. And that's exactly what happens there. So that should be a pretty good explanation in general of what's going on inside of a confidence interval. I think you can see that actually calculating the confidence interval is quite straightforward in TC Stats. It's no big deal at all. It's going to take a little bit more effort to try to understand what's really happening and how to interpret those confidence intervals.